Good morning. This is Professor C. Ravikumar Reddy, CBIT. This session we'll talk about uniformly varying load. Now you see member AB with a uniformly varying load. Okay, so the load may also be called as trapezoidal load. Right, what you see here is a trapezoidal load. At A, the load value is 2.5 kilonewton per meter, and at B the load value is 6 kilonewton per meter. Okay, yeah, now this member is in equilibrium, and this force system is a general force system. Okay, so let us see how we solve the support reactions at A and B. Okay, yeah, let us draw free body diagram first. So I'll just drop the point A down, also point B, just drop it down. Now we draw member AB again. Now by removing hinge at A, we can have two reactions. So I'll name them as R1 and R2. Then by removing roller at B, we'll have one reaction. I'll call that as R3. Okay. The span of the beam is 9 meters, or the length of the member is 9 meters. Okay. Yeah. Now the question is how to reduce this load into a point load. Okay. Right. There are two ways of doing that. You can straight away reduce the entire trapezoidal load into a point load, or there is another way which is simple, to divide this given load into two loads. Okay, just divide this load. Okay, it's like dividing the trapezoid into a rectangle, what you see here, and a triangle. Okay, so now this height of this triangle, what you see here, this total is 6. Okay, then where this height is 2.5, the rectangle height is 2.5, right? The rest of the height is 3.5 kilonewton per meter. Okay, so this is how this is being divided. Okay, now you have two loads. One is the uniformly distributed load. This is divided into two loads. One is uniformly distributed force, the other one triangular force. Okay, right? So now we will calculate the point load from the UDL first. So consider uniformly distributed force, which is a rectangle. So the total force will be area of a rectangle, which is equal to 2.5 times 9, which comes to 22.5 kilonewton. Okay, yeah, now the UDL is converted to a point force, point load, or point force. Okay, where to apply on this beam? It was distributed for 9 meters. Now you have converted that into single point load. 22.5 is now the equivalent load to this uniformly distributed force. Okay, you see the area of rectangle gives you the total force. 2.5 is the height of this rectangle. 9 meters is this length of the rectangle. Yeah, so this will act at center of load span. So here the load span is 9 meters. So it will act at center, which means half of 9 meters. So let us apply the point load or point force, which is 22.5 kilonewton. Okay. So now this is the equivalent force to the uniform force here. Yeah. So now what is remaining is triangle load here. So how you write point force for a triangle force? So the triangle force is again area of triangle will give you the total force value, half base height, so which comes to 15.75 kilonewton. Where this will act is the question again. So it is going to act at centroid of triangle. Centroid. Okay. Yeah, for rectangle, the centroid itself is center. So we write center here. Whereas for triangle, center is different, centroid is different. So we'll write centroid. So the centroid is, okay, you might have learned from the centroid chapter. The centroid of triangle is 1/3 of height from base. So now the triangle, what you see here. So this is the triangle here. Okay. Now if you say this is the base and this is height, because you want force location in x direction. So this direction will be your base of triangle, height of triangle. This will be the base of triangle. So h is now 9 meters for this triangle. This is the base. So 1/3 from base. So divide this into 3 equal parts. Okay, like h by 3, h by 3 and h by 3. So h is 9 meters. So each one is 9 by 3, which is 3 meters each. Okay. So the centroid will be at 3 meters from B. Okay, like here. So you drop that point and mention the force. What is the value? 15.75 kilonewton. Now the distances you see, this distance for uniform force, it is half the 9 meter, like 4.5 meters. For triangular force, it is 3 meters from here, or 2h by 3 from apex. This will be the apex of triangle, 2h by 3. So this is how we reduce a trapezoidal load into point loads. Okay. Yeah, now the rest of the procedure for solving the beam is same. Okay. Yeah, here you see the member AB is now having total 5 forces, out of which 2 are applied forces and 3 are reactions. Okay, so now you keep writing the equilibrium equations. Okay, so writing equilibrium equations, apply equilibrium equations. Okay, so writing the first equation, sum of x forces 0. Take any direction as positive. I consider rightward acting forces as positive. So if you see the member, there is only one horizontal force. It is R1. So R1 is equal to 0. Apply second equation, sum of y forces 0. Take any direction as positive. So I take upward acting forces as positive. You see the member, R2 is acting upward, R3 upward, and these two are downwards, 22.5 and 15.75 downwards. Okay, so R2 plus R3 minus 22.5 minus 15.75 is equal to 0. So simplify, R2 plus R3 is equal to 38.25. Okay, so this is the relation between R2 and R3. Then we have third equation, sum of moments is equal to 0. So pick one point as moment center. I pick A. Pick a direction. I pick clockwise positive. Whichever you like, you can pick like anti-clockwise or clockwise. So writing moments. Okay, now you see I pick this as moment center. So 22.5 into this distance you see here is 4.5. So moment center and the perpendicular distance. And this is trying to rotate this member by clockwise direction. So 22.5 into 4.5 clockwise. 22.5 into 4.5 clockwise positive. Next force. 15.75. Distance from A is 6 meters. And again, this force is also trying to rotate this member clockwise. So 15.75 into the distance from A is 6 meters, clockwise positive. So the leftover force is R3 only. Yeah, this is causing anti-clockwise rotation like this. Force multiplied by the distance 9 meters from A. So R3 into 9 negative is equal to 0. Okay. Yeah, so from this we get R3 value, which is equal to 21.75 kilonewton. Okay, right. Now substitute this R3 into this equation. We get R2 value. I'll write it here. R2 is equal to this 38.25 minus 21.75 will be 16.5 kilonewton. Okay, so you can see R1 is 0, which is horizontal reaction. R3 is the right support reaction. Here is the reaction, right support reaction, which is 21.75 kilonewton, whereas R2 is 16.5 kilonewton only. Why the right hand support reaction is more? You see the forces From the center of the member towards right, there is more force. Okay. Towards left, there is no force at all. Towards right, there is a force. So because of this heavy force in this portion of the member, this reaction is more. Okay, more is the force towards the support, more will be the reaction. Okay, yeah, this is how we handle the uniformly varying load, or the other way called as trapezoidal load, trapezoidal force or load. Okay, right. Thank you. We'll be back with the other content.